Much for inviting me. Very happy to be here. Yes, and the recording can begin. Very happy with that. So give me 1 second to share my screen. Okay. Awesome. So I'm going to say before I start that do feel free to ask questions throughout the talk. You can just put questions in the chat. Or if you prefer, you can also raise your hand. I'll try my best to get to questions as I go, and I'm very happy to kind of dive into some material in more detail, or to pause or to revisit things. So please definitely ask questions if there's something that's confusing for you or something you want to know more about. And so the topic for today is this idea of what we call graph representation learning. So you can think of this as trying to build machine learning methods that can operate on graph data. So the intent with the talk today is to give a bit of an introduction to this area. I'm not going to cover all of the most sophisticated techniques in this space. In preparing this, I have various material. I've given a number of tutorials, and I aim to try to give the foundations. And I'm very happy to give pointers for further material that you can look into if you find this space interesting. So hopefully I struck the balance in terms of having this be interesting, but also be accessible for the audience today. So first off, there's this question of why do we actually want to do machine learning on graph data? So graphs are really a general language for modeling or describing complex systems. So if we're thinking about what a graph is, we can contrast it with maybe our usual machine learning scenario. So usually when we're thinking about learning or running statistics on some particular set of data, we think about having a set of independent points. And in fact, for most machine learning algorithms, this assumption that we have a number of independent points is really critical, right? So we usually are thinking about, okay, how can I classify all these different points? How can I cluster these different points and so on? In contrast, when we're thinking of a graph setting, we're not considering a set of individual points, but really the whole object that we're trying to actually do learning upon is bound up in the interconnections or the relationships between these points. So rather than a set of independent data points, so rather than thinking of maybe a set of individuals as just unique individuals with some properties about them, maybe we have some attributes like people's age, where people live and so on, we're trying to make some predictions about them. That would be this kind of independent traditional machine learning view. But if we're thinking about the graph view of things, then we're considering not just these individuals, but the relationships between them, so their social networks and so on. And in terms of the types of real world data sets that I work with in my work and the kinds of graph data sets that are quite popular. So one very popular example that I just alluded to is social network data. So here we have the nodes or the vertices in our graph corresponding to individuals, and then we have edges which represent the relationships between individuals, maybe friendship, maybe we have edges representing whether or not people are enemies with one another and so on. Another very popular type of data is information networks, also called knowledge graphs. So here we have that the vertices or the nodes in our graph, they correspond to some kind of content, some kind of information. Maybe it's even an individual, a place, a location.
I apologize. I accidentally missed the admit button for the waiting room.
Totally okay. So yeah, so in these information networks or knowledge graphs, it's really a way of representing general structured knowledge as graphs. So a great example of this in the real world is when you Google something and you get that panel on the side, that's this little info panel. So say you Google Barack Obama, you get this information panel that says Barack Obama was the president of the United States, was born in Hawaii, and so on. This knowledge that is used to populate this little information panel actually comes from what's called the Google Knowledge Graph. And so basically within this knowledge graph, you might have an entity representing Barack Obama. You're going to have a relationship that says born in, and then Hawaii, president of United States, and so on. So if you're familiar with things like relational databases, all kinds of objects like that, you can represent many of these things as graphs. In addition to that, some other very interesting data sets include things like economic networks. So here you have nodes maybe representing countries and edges representing trade relationships, biomedical networks. So here you might have nodes representing proteins, edges representing protein-protein interactions. You can really think of the internet at large as being a large graph or network where you have interconnections between different websites. And then, of course, something that's very relevant in Montreal, given the Montreal Neurological Institute being here, is thinking about networks of neurons as being represented as graph structures. And so you can see there's a very broad, large amount of diverse data sets that we can think about as graphs. And so why are graphs an exciting thing to look at? And I should say that trying to do machine learning on graphs has been a very increasingly popular object of study in the past few years. So one of these reasons for the growing popularity behind this area is the fact that graphs are really a universal language for describing complex data. I mentioned this before, but you can use the same abstract data structure, right? The fact that you have nodes and you have relationships between nodes, and this can be applied to social networks, to things from biology, to things from transportation, and so on. It's this nice shared vocabulary that we have across all these different fields. Another very important fact that has driven the adoption of these techniques in recent years is data availability. So over the past, say, 5 to 10 years, there's been a huge increase in the number of data sets that are available for doing machine learning on graphs. So data sets coming from large social media sites, data sets coming from biology, and so on. And then there's also been a very high amount of impact for these techniques. So obviously, graph-based machine learning is extremely important in many social networking contexts. So for driving, say, recommendation systems. So for example, if you ever worked on Pinterest or been on Pinterest, I don't know if you work on Pinterest, but if you ever use that website where you pin content and you use it to save it for later. So one way you can think about Pinterest is actually being a really big graph where you have pins that people are pinning this content, and then you have boards or collections of these pins, and then you have users who are creating these things. And you can actually think about these kinds of social networking or social media sites as graphs. And in fact, the kinds of graph-based machine learning techniques I'll discuss today, and actually some things in my thesis, were used to power the recommendation engines on these platforms. So for example, Pinterest actually uses some of the techniques from my prior work to power their recommendation system and some of the things we'll talk about today. And then another really exciting direction where we see a lot of impact is on computational drug design. So this is an area where I'm quite active in now. And this is where we think about trying to understand biological systems from the perspective of them being represented as graphs. And this has led to a lot of really exciting results, and even some exciting results, for example, for trying to come up with new treatments for COVID-19. Okay, so what I'm going to start with now is a bit of a discussion of what are some of the classic machine learning tasks that we do on graph. So to give a high level overview, the kind of things that we do on graph data include trying to classify nodes, so predict some information about the nodes in a graph, trying to do what we call link prediction or predicting relationships between nodes. We also sometimes try to detect communities within these graph or network data sets. And also sometimes we even try to compare whether or not two graphs or networks are similar to one another. And I should also say that I use the term graph and network somewhat interchangeably. These two terms are used just depending on what community you're in. Usually graph is a bit more of the mathematical terminology, whereas in more of the applied areas, people tend to call these network data sets. But I'm going to focus on these first two tasks, these ideas of node classification and link prediction, and discuss them in just a little bit more detail. Okay, so this idea for node classification, here, we're going to be given an input graph as our input, but we're going to have labels associated with only a subset of the nodes in our data. So for example, we might have a social network, say corresponding to a website like Twitter, and we might have information that some of the users on this platform are actually bots. Well, we're not going to know this about all of the users, right? So we're going to have some labeled information about a small subset, of the users on this platform, so labels on a small subset of the nodes, but we're not going to know the labels on all of the nodes. And the idea is that we want to try to apply some kind of machine learning algorithm that can allow us to infer the labels over the entire data set. So I mentioned one application of this, which is maybe, say, detecting bots on a social network. Another really important application of this is actually classifying, say, the function of proteins in the interactome. So you can represent the interactome, which is all the proteins, say, in the human body, based on the interactions they have with one another. And then a really critical challenge is actually trying to understand the function of these proteins based on their position within this giant protein-protein interaction network. So the other very canonical machine learning task on graphs is what we call link prediction. Here again, obviously we're given a graph as an input, but now rather than having some uncertainty over node labels, instead we actually have uncertainty about the relationships between certain nodes. So we know maybe that some edges in this graph exist. We know that some users are friends, say, but we're uncertain about the existence of other edges. It might be the case that maybe two users are friends and maybe they're not. And we want to use a machine learning algorithm to figure this out. So again, as I alluded to a few minutes ago, a very important real world example of this is content recommendation. So you can think about the graph between, say, content on one side. So if you're looking at Pinterest, you have content that people are looking at, and then you have the collections that people are putting this content in. So we can think of this as a bipartite graph. So maybe you have users on one side and content on the other. And we're trying to maybe classify or predict what content a user is likely to interact with. And this is a very, very popular task in many, many real world systems, things like Pinterest, Facebook, Twitter, and so on. Okay, so now we're going to get into what exactly the representation learning aspect of graph representation learning is. So in the typical classic machine learning lifecycle, the idea is that we go from some raw input data, we come up with some structured, some feature representations of this, we apply our learning algorithm, and then after applying this learning algorithm, we then have our model. And one of the very critical traditional things we have to do is this feature engineering step, where we take our raw data and we apply some kind of feature engineering to get our structured representation, which we can then use in our downstream tasks. And as I'm sure many of you are familiar with, there's been a big move away from this kind of very traditional life cycle in machine learning, and this idea that we actually want to get away from this feature engineering step. So rather than doing all of the work of trying to handcraft some way of representing our data, we instead try to design learning algorithms that can directly learn from raw inputs. So things like convolutional neural networks for vision data, or things like recurrent neural networks for text data, which you might have seen in some of the other talks on computer vision and natural language processing. So if we're thinking about this within the context of graph data, we can really think of the challenge here of trying to have some kind of task independence, so some general way such that we can map graph data to useful representations. And by useful representations in particular, what I mean here is a way to map the nodes in our graph to low dimensional vector embeddings. So mapping the nodes in our graph to some vectors that then we can use in our machine learning algorithm. Because all of our machine learning algorithms at the end of the day, they take vectors, lists, arrays of numbers as input. So we need to have some way of representing our graph as these vectors. And just to give an example of what this can actually look like, so what I'm showing here is on the left is a very famous social network. It's called the Zachary's Karate Club network. So it's a real social network of different people who were at a karate club, so who practice karate together. And the edges indicate whether or not people were friends with one another. And it's quite famous because it's a famous sociological study where basically the sociologist was able to predict how this karate club was kind of going to split apart into two competing groups based on the structure of the social network. So it's a very famous classic sociological data set. What I'm showing here is how this data set, where what I'm showing in colors is the different communities that are underlying within this data set. So on the left here is the graph representation. And then on the right is an embedding or a representation of this graph within a two-dimensional space. So every node on the left is now projected onto a two-dimensional point on the right. And the important thing is that this two-dimensional projection is preserving some of the really important things like the community structure within this original input network. And I want to highlight, it's kind of a subtle point, but it's possible to draw this network, which has, I think, just around 30 nodes on a two-dimensional plane. There's some crossing over of edges and so on, but that doesn't mean that this picture on the left is a two-dimensional representation of this network. So in general, if I have a network or a graph that I'm given, and I'm trying to think about what is the inherent kind of dimensionality or the size of that graph when it's given to me, basically to represent every user in that or every individual in this social network, I need to think about who are they connected to. So there's 30 possible people they could be connected to. So really the dimension of this input is equal to the number of nodes. So graphs are actually really high dimensional objects. So if you have, say, the social network on Facebook that has maybe over 1 billion users, really there's a kind of a billion dimensional object. And what we're trying to do is trying to represent this in a much smaller dimension. And again, this is kind of a Tory example. We're going from a 30 node, so a 30 dimensional network down to 2 dimensions. But in most real world examples, we're going from social networks or biological knowledge graphs that might have 1 million nodes and trying to represent them using maybe 100 dimensional vectors. And I see that there's a question. That's a great question. So what are the axes on the output graph? So the axes here on the output graph don't really have a predefined interpretation. So if you're familiar, for example, with techniques like principal components analysis, perhaps, or doing things like finding the eigenvectors of a matrix, the two dimensions on this graph are pretty analogous to thinking about the dominant principal components or the dominant eigenvectors of the network. And actually, in some of the examples that I'll talk about in just a few slides, that's exactly what they are, but not always. So that's kind of the way to think about it, is that these dimensions don't correspond necessarily to anything interpretable, but just like looking at the the dominant eigenvectors of a matrix, so the eigenvectors that have the largest eigenvalues, or the dominant principal components of a data set, these dimensions are the dimensions that are capturing the most important variance in the network. So in particular here, these are the dimensions that are most important for actually capturing the community structure within this graph. But that's not always going to be the case. It's going to depend on what kind of representation learning algorithm you use. But typically, what they're doing is something very, very similar to principal component analysis. And so one way, I don't actually put it this way in any of the slides, but I think a very useful way of thinking about all the techniques I'll discuss today is basically this idea of how can we do principal component analysis, or how can we get the eigen decomposition of a graph, is really what we're doing. It's a great question. Okay, so I want to just highlight for a second why representation learning on graphs is hard. And I want to do that by contrasting a little bit with some of the other data that we tend to work with, say in machine learning, and especially in things like deep learning. So you may be familiar with techniques like convolutional neural networks, which are designed to work on image data and have worked very well on image data, right? One of the great success stories of machine learning and deep learning over the past decade has been things like convolutional neural networks, as well as in the case of working with text or sequence data, so time series or text data, things like recurrent neural networks or LSTMs, long short-term memory networks, which are recurrent neural networks that process sequential data. So in both of these instances, we have really powerful deep learning algorithms that can allow us, in the case of images, to learn powerful representations of images, and in the case of sequences or text, to learn powerful representations of text. But the issue is that there's no simple way to apply these existing techniques to general graph data. And one way of thinking about this is that convolutional neural networks, they really only work on grids. So images, right, are basically two-dimensional grids where you have pixels. And so convolutional neural networks actually generally, and this is like a true formal statement, convolutions work on grid data, or generally they can be higher dimensional grids, but they can only work on grids. And similarly, recurrent neural networks can really only work on sequences. So these techniques are very powerful, but they don't work for all graphs. They only work for a very special case of graphs. And the issue is that when we're thinking more generally about graph data, there's a lot of complexities that we have to deal with. So one of these issues is the fact that graphs can have really complicated topological structure. So if we're thinking about a grid, one thing that's really nice about a grid is that we can very easily think about, say, having a sliding window over this grid. And it's very easy to think about how that works. And there's this idea of what we call spatial locality, which is the idea that, okay, if I have one node that is a neighbor of another node or kind of close to another node, and that node's close to another node, then I know exactly how far apart these other two nodes are, right? There's this really simple structure, geometric structure to grid data. And this is what we leverage when we do things like convolutions, where the way that convolutional neural networks work is we're basically kind of applying a sliding window or a patch over the grid. The issue with more general graph data is things can get pretty complicated. So for example, you can have a graph where every node is neighbors with every other node. Or you can have a graph where maybe it's a star. So you have one node in the middle that's connected to everybody else and they're all not connected to one another, right? So there's no easy way of thinking about how can you have a patch or this kind of notion of spatial locality on these more general kinds of graph structures. Another issue, which is actually kind of the most important fundamental mathematical issue, but it's a little bit hard to wrap your head around. I won't go into too much detail on it, is this idea of what's called the isomorphism problem. So this is the issue that when I'm given a graph, there's no fixed ordering for the nodes in this graph. And you can think about this, that when you're given an image, there's always a fixed orientation for that image, or generally, right? So images typically come with an orientation. We know what direction's up, what direction's down, what direction's left and right. But when we're given a social network, we don't know which node in the social network is the bottom node or which node is the top node. And this is kind of this idea that if we're going to, say, try to represent a social network or a graph generally, say in an adjacency matrix, where this is a matrix that has number of nodes by number of nodes, and every entry says which nodes are connected, there's no canonical or standard way to order the nodes in this adjacency matrix. Again, this is different from things like images. In images, we have kind of canonical directions. We know what's up, what's down. In graphs, there's no way of knowing what's up and down. And this is actually really challenging. And in fact, it's an interesting point that even trying to tell whether or not two graphs are the same. So I give you graph one, I give you graph two, but we don't know, there's no fixed canonical kind of orientation for these things. I give you two different graph data sets represented as, say, adjacency matrices. And all I want to know is, are these the same graph? And that's actually a problem that is computationally hard, is NP indeterminate. So it's believed to not be solvable in polynomial time, which basically means it's really hard. It's as hard as trying to factorize integers, which is really hard because that's how we base a lot of cryptography and things like that. So this is weird point that graphs are really hard to work with, because even knowing whether or not two graphs are the same is computationally challenging and can take exponential time to understand. And then lastly, a point that is a little bit more kind of applied, but still very important to think about, is the fact that most of the graphs that we want to work with in practice, they also change. They involve all kinds of multimodal features, so images and text associated with the nodes. So there's a lot of challenges. Graphs in some ways are at least as hard as working with text and images, but they're even harder. Okay, any questions at this point before we dive into some of the methods? Okay, So what I'm going to discuss for the remainder of today's talk is this idea of what we call embedding nodes. So this is the kind of classic canonical way of representation learning on graphs. And the intuition here, and I alluded to this before, is that we want to find some kind of embeddings or representations. So we can map every node in our graph to a d-dimensional input, and we want this embedding space that we're optimizing to reflect the original structure of the graph, where ideally we want nodes that are similar in the input graph to also be similar or close together in this embedding space. So just to make things a bit more formal, we're going to assume that we have a graph. So a graph is given by a vertex set. So this is a set of nodes, as well as the adjacency matrix. And we can assume this is binary. So this adjacency matrix has one row for every node and one column for every node. And there's a 1 in this adjacency matrix if these two nodes are connected to one another. So basically, this adjacency matrix is just telling us which nodes are connected to one another. And in today's talk, we're going to assume that there's no other extra information. There are many techniques, more advanced techniques that can leverage, say, node features and other complicated information along with the graph structure, but we'll leave that as kind of future reading for those who are interested. So again, the goal is what we're trying to do is encode the nodes from our input graph or our input network into some low dimensional embedding space. And typically what we want to do is we want the similarity in this embedding space, which we usually represent using the dot product, is we want the dot product, which is kind of like the distance in our embedding space between nodes, to approximate some measure of similarity in the original network. So we can think of this mathematically as we're saying that I want the similarity of nodes u and v in my original graph to be approximated by the dot product. So I just have a vector representing node v and a vector representing node u, and I'm taking the dot product. So just the element-wise multiplication of these things and then summing all the entries together, which is something that's basically analogous to the distance or the similarity. It's kind of 1 minus the distance between these two vectors or these 2 points. Now, of course, this is very generic, very high level, and what we need to define and what we're going to discuss in more detail is how we actually define this notion of similarity in the input graph that we're trying to approximate, as well as this idea of how we're actually encoding these nodes. So in general, when we're trying to learn node representations, the way that we do this is first off, we have to define some kind of encoder, i.e. some kind of mapping that maps our node to low dimensional embeddings. We need to have some kind of similarity function. So what is the graph similarity that we're trying to approximate with our learned representations? And then we need to then optimize our parameters so that our node embeddings actually approximate this desired measure of similarity. So the key components here being the encoder, which mathematically the encoder takes a node ID, it takes the V as input and gives us a d-dimensional vector that represents this node. And then we have our similarity function. It takes a pair of nodes and says how similar they are. And this is what we're trying to approximate in our embedding space. So the simplest and probably the most popular approach for encoding nodes, and what I'm going to focus on today, is what's called a shallow encoding technique. So the idea here is that our encoder is just what we call an embedding lookup. So the idea is that we're going to have a big matrix where every column in this matrix corresponds to a different node in the input graph. And then when we want to embed a particular node, we're just going to look up that node's row, or sorry, that node's column in the embedding matrix. So it's maybe a bit easier to understand visually, right? So it's a pretty simple thing we're trying to learn in some ways, is that we're basically saying that for every different node in our input graph, I'm going to have a unique vector embedding for that node. And we can think of this as being contained within a big embedding matrix. So if we have, say, V nodes in our input graph, this embedding matrix is going to have V columns. And then if we have d-dimensional embeddings, this matrix is going to have D rows. And if we want to say, oh, get me the embedding for a particular node, I'm going to do that by just looking up that node's column within this embedding matrix. And the idea here being that each node just assigns its own unique embedding vector. And this is a technique that's used in a number of approaches. So things like techniques you may have run into that we'll talk about today, like node to vec, and also a technique called deep walk. So this is what we're going to focus on today. There are more advanced encoding techniques that are based on deep neural networks, things like graph neural networks, but we won't cover that in detail today. Okay, so that's this idea of how we define the encoder function. But now how do we then optimize this embedding matrix, right? So we can say, okay, we're going to represent all of our nodes with some low dimensional embedding, but how do we actually know what's the right embedding to use? In particular, should we try to optimize embeddings, for example, so that the two nodes have similar embeddings if they're connected, maybe if they share neighbors or so on. So we'll talk about a few options in the next few minutes. And in particular, we're going to talk about three kind of classic approaches. One that I call adjacency-based similarity, one's called multi-hop, and then one that's called random walk approaches. And what I'll talk about today is largely based on this review paper that I wrote in 2017. Okay, so first off, let's think about this idea of what we call adjacency-based similarity. So here, the similarity function, so what we're trying to approximate is the edge or the edge weight between two nodes in the original graph. So in particular, let's imagine that we have our adjacency matrix. So each entry in this adjacency matrix, so if we have the adjacency matrix and we're looking at the row corresponding to node U and the column corresponding to node V, this tells us are node U and V connected? And perhaps if it's weighted, how strong is this connection? So what we're trying to say is we want the embedding of our nodes U and V, their dot product to approximate their entry in the adjacency matrix. So what we're saying is that get the embedding for node U, get the embedding for node V, take their dot product, and ideally we want that dot product between these two node embeddings to approximate the entry for node UV in the adjacency matrix. So if node U and V are connected, this dot product should be close to 1. If they're disconnected, this dot product should be close together, or sorry, should be close to 0. And what I'm showing here is that we're taking the distance. So this is just the Euclidean distance between this dot product and the entry in the adjacency matrix. We're taking the square of it because that generally makes the math easier. And then we're summing over all pairs of nodes. So the loss, what we're trying to minimize when we try to optimize our node embeddings, is going to be the sum over all pairs of nodes. What's the distance between the dot product of their node embeddings and their entry in the adjacency matrix? So how would we actually optimize this in practice? Well, one thing that can be done, if you're familiar with frameworks like PyTorch or TensorFlow and so on, is we can use these automated gradient descent techniques. So these are black box kind of optimization algorithms where we say, okay, I give you a loss. Now find me the parameters that minimize this. That's one thing we can do. Another thing that we can do actually specifically just for this adjacency-based similarity is that I did mention earlier that you can think of these node embeddings as kind of corresponding to something like the principal components or the eigenvectors. And in fact, for this particular formulation, the node embeddings that we're learning can actually be determined by getting so if we're looking at d-dimensional node embeddings, by getting the top d eigenvectors of the adjacency matrix A. They're actually what's called the singular vectors because we're working with not necessarily a square matrix, but the basic idea is the same. So basically, we have to do an eigen decomposition of our adjacency matrix, and that's what gives us our node embeddings. So again, in this special case, that's how we can interpret our learn node embeddings, is they're kind of like the principal components of our adjacency matrix. But there are some issues with this approach. So first off, it's quite expensive in terms of its runtime. Another issue that I'll focus on is this issue that it's really focusing only on direct connections between nodes, right? So we're saying, okay, I want node U and V to have a dot product of 1 if they're connected, 0 if they're disconnected. But what if they're just kind of close together, right? So ideally, we would want, in this example down here in the bottom left, we would want the blue and green node to have more similar representations than, say, the blue and the red node, because it really seems like the blue and the green node are closer together. And this approach of only trying to directly optimize whether or not two nodes are connected doesn't really capture these more general notions of neighborhoods between nodes. So we can address this by using what are called multi-hop similarity methods. So the idea here is that we're going to consider k-hop neighborhoods, right? So if we're looking at this red node here, we can think of as one-hop neighbors as being its direct neighbors, so the nodes it's connected to. Its two-hop neighbors are going to be nodes that you can reach on paths of length 2, starting from the red node, and the three-hop neighbors, and so on. And what's actually very useful is that the one-hop neighbors, these are given by the entries in our adjacency matrix. So if we look at a particular value in the adjacency matrix, that tells us whether or not two nodes are one-hop neighbors, whether or not they're connected. But what's interesting is that if we take the square of the adjacency matrix, so we take the adjacency matrix and multiply it by itself, and we look at the entries in this squared adjacency matrix, these entries are going to be non-zero if nodes are two-hop neighbors with one another. And similarly, if we take the third power of the adjacency matrix, this now contains information about which nodes are in the same three-hop neighborhood as one another, and so on. And we can use this idea and actually try to, instead of just optimizing embeddings that represent direct connections between nodes, we can actually learn embeddings that represent powers in the adjacency matrix. In practice, the formulation that's worked quite well, for example, in what's called the GRARAP paper, which is for graph representations from Cow et al. It was actually a little bit more complicated. They did some logarithmic transforms and some other shifts and things like that on top of the adjacency matrix. But the basic idea is that we're trying to learn something that's like a power of the adjacency matrix. And again, here you can think about it like we're trying to find the principal components of these powers of the adjacency matrix. Another option, which is actually quite elegant, is we can just try to come up with some measure of overlap between node neighborhoods, right? So here we can say, okay, for the blue node and for the red node, they share two neighbors. So they're kind of close together. And you could say, okay, they share two neighbors, and let's normalize that by how many nodes are in their union, right? So let's take the intersection here, two nodes in this intersection, and divide that by the size of the union of their neighborhoods, right? Which contains 1, 2, 3, 4, 5, 6, 7 nodes. And this is the basis for overlap functions that are called the Jaccard similarity, also what's called the atomic Adar score. And there's many variations of how we can quantify the overlap between two nodes neighborhoods. And what we can do is if we have some way of quantifying the overlap between the node neighborhoods of different nodes, we can make a new representation of our graph using what we call an S matrix, where an entry in this S matrix says, what is the neighborhood overlap between nodes U and V? And now, just like our prior approaches, we can try to learn some low dimensional approximations. We're going to learn some node embeddings. So that in this case, the dot product between the embedding for node U and the embedding for node V is going to approximate the overlap between the neighborhoods for nodes U and V. This is a nice approach. It's very flexible, works in many cases. So the basic idea so far is that we've defined these pairwise node similarities, and then we're trying to optimize low dimensional embeddings, right? So what we're trying to do is we're trying to say, give me low dimensional embeddings so that, say, the dot product between them, the distance between the node embeddings dot product is small compared to the overlap between these nodes. So the dot product between the embeddings for node U and V should approximate the overlap between their neighborhoods in the original graph. Generally, these approaches can be quite expensive. And another issue with them is that they can be kind of brittle, right? And we have to think, okay, well, what neighborhood overlap technique should we use? And in practice, these approaches work okay, but they're not the best approach. And in terms of what's actually tends to be the empirical state of the art for these kinds of shallow embedding approaches is actually what we call random walk approaches. This will be the last set of techniques I'll cover in detail today. So In these random walk approaches, we're going to have a similar kind of idea. We still want to have it so that we learn low dimensional embeddings for our nodes U and V, so that these approximate some information about our graph. But instead of trying to rely on the direct adjacency matrix or some power of the adjacency matrix, what we do with random walk embeddings is we try to optimize our embedding so that the dot product between the node embedding for node U and V approximates the probability that these nodes co-occur on a random walk over the graph or network. So if we have a random surfer, as people often call it, say, you can think about having um, a little agent that is randomly going from node to node based on who's neighbors and just randomly choosing a neighbor of every node. We want to have our node embeddings encode the probabilities that two nodes co-occur on such a random walk. And so the way that we do this is that we start by running random walks from all the different nodes in our graph. So we're going to say run a random walk starting from node U in our input graph, and say we'll run a random walk using some what I call random walk strategy. So maybe we're just doing random uniform walks of length 3. So we just take 3 random steps. We end up at some other node V. What we're going to do is we're going to do this over and over, and enough so that we can actually estimate the statistics of what's the probability of seeing node V on a random walk starting from node U. And then we want to optimize our node embedding so that the dot product, or the angle between these node embeddings, is proportional to these random walk co-occurrence probabilities. And what's nice about this random walk approach is, first off, it's very expressive, right? So we now have this flexible kind of stochastic definition of node similarity, rather than just saying, oh, nodes are similar if they're connected or if they're two hop neighbors. We have a much more fuzzy and flexible notion of whether or not nodes are similar to one another. Another very important point, is more of a technical one, is that you can actually implement and run these random walk node embedding approaches in a much more efficient way compared to the techniques I was discussing earlier. So we don't need to enumerate over all pairs of nodes necessarily. So to give a bit more technical detail in terms of how these random walk techniques work, so first, we're going to run short random walks starting from every node in our input graph using some random walk strategy R, right? You can think of this for now as just saying, okay, let's run just completely random, uniform, random walks over our graph. And for each node, we're going to collect the set. It's actually technically a multi-set, because in a set, you can only have every entry represented once, but in a multi-set, you can have duplicate entries. So this is going to be a multi-set, which says, what are all the nodes I've seen on a random walk starting from node U? So if I've seen node V 10 times on a random walk starting from node U, node V is going to occur 10 times in this set, NRU. And then what I'm going to do is I'm going to optimize my embeddings according to the equation shown down here. And the basic idea is that, okay, I'm going to sum over all nodes in my graph. That's the first step. The next step is that for each node, I'm going to sum over all of the nodes that I saw on random walks starting from this node. And then this term here is a very classic thing we do in machine learning, which is that we're trying to, in this case, minimize what's called the negative log probability. I think it's best to think about that. We're trying to learn embeddings that give the highest possible probability to these random walk statistics that we end up seeing. So the intuition here, you're trying to optimize embeddings to maximize the likelihood of random walk co-occurrences. So what this means in a bit more plain words is just to say that we want to have the embeddings that we're learning for our nodes reflect the tendency that nodes, the tendency of nodes to co-occur on short random walks. So if two nodes co-occur a lot on short random walks, so if I see node V many times on random walk starting from node U, the embeddings for nodes U and V should be similar to one another. And the way that we actually make this work mathematically is we use what's called the softmax function. And how this softmax function works is it allows us to get probabilities from these embeddings. So the idea is that if I want to say, what's the probability of seeing node V on a random walk starting from node U based on my embedding Z of node U, what I'm going to do is on the numerator, I'm going to take the dot product for the embeddings for nodes U and V. I'm going to put this through the exponential function. So what's nice about putting this through the exponential function is it guarantees that this is going to be positive. So no matter what the dot product is, it could be negative, but this is always going to end up being a positive value. And then on the denominator, I'm going to normalize, and I'm going to say, okay, I'm going to compare this dot product, the dot product between nodes U and V, to the dot products between node U and all other nodes in the graphs. So basically this is saying, okay, if I want to know how likely I am to see node V on this random walk, this is going to be proportional to the dot product between the embeddings for node U and V. But then I'm going to normalize based on the dot products between node U and all other nodes. This basically means that if the dot product between the vectors for node U and V is very big, I'm going to have a high probability of seeing node V, but only if the dot products for the other nodes tend to be small. So we're kind of looking at the relative closeness of these node embeddings to get these probabilities. And to put this together in terms of mathematically, what it looks like is we end up again summing over all nodes, summing over all, looking at the neighborhood sets for all of these nodes. And then we're trying to use this softmax term, and we're trying to maximize the predicted probability that U and V co-occur on random walks based on this softmax formulation shown down here. Okay, so I hope that that was sufficient explanation to get the high level idea. And here I want to emphasize that, well, how do we then actually optimize this? So in principle and in practice, what you would do is this gives us your loss function. So we're trying to find node embeddings that minimize this loss function. And we do that by running techniques such as gradient descent, which typically are implemented in off-the-shelf optimization libraries, things like PyTorch or TensorFlow. So we specify our loss function, and then we use optimization routines to try to find the node embeddings that minimize this loss function. So far in the last few minutes, we discussed how we can optimize embeddings using random walk statistics. But one question is, well, how do we actually run these random walks, right? So what kind of random walks do we do? So one simple idea of what I've been discussing so far is let's just run fixed length, completely uniform random walks starting from each node. This is called the deep walk approach. This is also actually the idea that underlies what's called the PageRank algorithm. So what used to be the algorithm that Google used to rank search pages, I'm sure they still use it somewhat. But basically the idea is that if I'm thinking about a random walk over the internet, you can think of how important a web page is relative to some other web page as basically being the likelihood of running into web page B on a random walk of a fixed length starting from web page A. So this idea of kind of running random walks in this way is very important, not just for these kind of representation learning tasks, but a really classic and important approach in network analysis. And usually what people will do is think about just completely uniform random walks. But we can actually do some more interesting things. And this is an approach that was called the node to vec approach. And the idea here is that we want to use more flexible biased random walks that can actually trade off between what we can think of as more local versus more global views of the graph. So if you're looking at this particular graph here, where you can see that there's kind of two different communities, right? We have a community on the left and a community on the right. And if we think about how we can explore this graph, there's really two canonical exploration strategies, right? So one is that we could say we're starting at node U, we can explore all the neighbors of node U first. We typically call this a breadth first search, which you may have encountered before. But the idea is that in a breadth first search, we're really kind of emphasizing getting a local view of the graph or network first. As an alternative, you can think of more of a depth first type algorithm, where rather than exploring all the neighbors of node U first, we're actually going to, in a depth first way, say, okay, I'm going to go to this neighbor, and then I'm going to go to some other neighbor of that neighbor. And I'm going to kind of explore deeper and further away into the graph. And we can use this intuition and think about running random walks that are more akin to BFS, or random walks that are more akin to DFS. And this can allow us to trade off between learning more local or more global views of our input graph. So again, the idea here is that we can use these different strategies, different biased random walks, to learn more local or more global views of our input graph. Whoops. And the particular way that this is done is that we have different probabilities when we're at a particular node of either exploring the neighbors of this node or doing a more DFS-like search. And these probabilities are usually denoted by P and Q. And here, what I'm just showing as an example of what this actually looks like in the real world. So this is a network of interactions from the Les Mis play, well, actually a novelization of the play. And so what we have here is that every node corresponds to a character in Les Mis, and the interactions between them are denoted by these edges here. So if two characters are both in the scene together, they're connected. And on the left, this is a representation learned using the node to vec approach, where we emphasize more of the local kind of microscopic view of the network. And what's interesting is that the embeddings, where I'm showing the embeddings that are similar, have the same color, is the embeddings tend to kind of reflect the structural roles. So we have characters who tend to be more bridge characters who connect different clusters are blue. These more isolated characters are yellow, and so on. In contrast, if we do more kind of DFS style walks, we end up learning representations that correspond to more of the community structure of this network. So we have that all of these nodes down here are kind of green, and we have all the red nodes over here, and so on. So we can learn representations of our graph that try to encode more of local structural features, or that capture more of the high level community structure. And there's been many different kinds of these approaches proposed in recent years. So just to summarize, the key idea here is that we want to embed nodes so the distances in our learned embedding space reflect some notion of similarity in our original graph or network. I talked about a few different notions of similarity that we can try to approximate, things like just trying to approximate the adjacency matrix directly, more multi-hop ideas, and then lastly, this random walk approach. I want to highlight now, just towards the end here, some limitations of the techniques I discussed today. So one issue is that when we're using this shallow encoding approach, where we're representing every node with its own unique vector, this is very expensive, right? If we have 1 billion nodes in our social network, say we're Facebook, we have to have 1 billion different vectors to represent each individual. This is kind of problematic. As a consequence of this, and a related point, these techniques are what we call transductive. So it means that if we have a new user join our social network, there's no easy way for us to get an embedding or a representation of this new user. We have to rerun our whole training algorithm. And it would be nice if we could get around this, if we could have an approach that could generate embeddings, say for new users just when they join the graph. And then lastly, these approaches are limited because they don't actually incorporate any feature information. They're only learning representations based on graph structure. So there are techniques that go beyond this, in particular techniques that are called graph neural networks. And the idea here is that instead of just using this embedding lookup idea, the shallow encoding idea that I mentioned at the beginning of this talk, instead, in these graph neural network approaches, our encoding function is a complex deep neural network that actually depends on the graph structure. Whoops. So I won't cover those in detail today, but if you're interested, I'm very happy to give resources or recommendations about where you can learn more about things like graph neural networks and go beyond the foundations I discussed today. So with that, I will close and take any questions. There's a minute or two left in case there are any. I do see there's one. Okay, there's a question from Keith here. Is that anyone use a graph neural network for an ensemble of neural networks, each making their own predictions? So do you mean to say kind of applying a graph neural network kind of on top of a set of neural networks? So kind of using the graph neural network to ensemble the individual neural networks? Ah, yes. There are some approaches I have seen in that vein. They've been typically referred to as kind of meta learning algorithms. I can't think of a specific reference off the top of my head, but I do believe that in 2019 or 18, I think it was 2019, that there was a paper by DeepMind that was doing something like this, and I've seen a few people discussing ideas in this space. So I can't give you a specific reference. I don't know if anyone's specifically done this for time series data that you've mentioned there, but I do know there's definitely been some things relating to that. And I think if you were to look for kind of keywords, I think things like meta learning or what's called few shot learning, I think is where I've seen this using graph neural networks is what I would try to Google perhaps. Can whole graphs be, yes. It's a great question, something I didn't cover. I actually had, and then I took out for time reasons. It's a question from Dylan about embedding whole graphs. Yes. So, for example, a really popular application right now is trying to represent molecules as graphs and then embed these molecule graphs to predict properties of molecules, like whether or not they're going to be useful drugs and things like that. Um, so typically what you do is you learn node embeddings and then you aggregate or pool those node embeddings together to represent the full graph. So the simplest thing you could do is you could just average or sum all the node embeddings, but there's also more sophisticated things you can do where you can, you can even imagine kind of clustering together the node embeddings in different ways, or there's all kinds of interesting aggregations that people do. But typically the pipeline is you learn node embeddings and then you aggregate or cluster or pool those node embeddings to represent the full graph. But it's a very active area of research is working with the whole graphs, but generally the whole graph algorithms use the node level algorithms as their building blocks.
Right, actually, so I asked that question and thanks for your answer. And a really quick follow-up, because you had quickly mentioned basically dynamical graphs, like really quickly. So is there a way to have people done this to basically learn whole graph embeddings as you just explained, but then as they evolve or, as a function of time to learn the sort of a manifold structure of these embeddings as a function of time?
Yes, so there is, so more of the dynamic setting is actually more common for node level prediction, because you can think about like recommendation systems or kind of online social networks, right? These are evolving graphs, and typically what people want is node level representations. It's less common for people to do dynamic graph level representations, but there is definitely some work. And I do believe, for example, that a former colleague of mine, Srijan Kumar, who is now at Georgia Tech, had some work on this. I don't know if it was, I'm pretty sure it was published, that we were discussing it some time ago. But definitely there's been some work in that space, but typically in dynamic graphs, just because of the applications, people tend to focus on node level tasks.
Okay, great. Would you have keywords for sort of manifold learning of whole graph embeddings?
So one of the things is that if you Google something like dynamic graphs, like dynamic graph neural networks, there'll be probably like 150 papers. So it's almost like a surplus rather than. So you'll be able to definitely find a lot. But I don't know of anyone that's specifically doing the kind of like manifold perspective you're looking at. You'll be able to find a ton just with the natural keywords. I would use something like dynamic and graph classification, perhaps.
Sure. Okay, thanks a lot.
No worries.
That's awesome. Thanks.
Does anyone else have any more questions? If not, I just wanted to thank Professor Hamilton again for giving a very informative talk and an accessible introduction to graph representation learning. Yeah, we're very happy to have you for our conference today.
Well, thank you. And I hope you all have a fun rest of the day.